I really wish I had an hour because I have this sort of story in my head about how we can go from self-driving cars and underwater robots and connect it to what's happening in MIT.nano. And so my impossible task is in 15 minutes. So I apologize for going fast. But I somehow feel like I'm the luckiest person in the world. I work in some really cool areas, so autonomous underwater vehicles, self-driving cars. I came to MIT as a postdoc in 1991 and joined the faculty in ocean engineering in 1996, and we merged with mechanical in 2005. And in the past few years, I went on leave and helped launch Toyota Research Institute. I'm still a technical advisor at Toyota for their self-driving car program. And in my academic life, I work on a problem known as SLAM, Simultaneous Localization and Mapping, where the goal is to build a map of an unknown environment while concurrently using that map to navigate. And SLAM is a pretty fundamental underneath the hood for how self-driving cars work, because self-driving cars use very accurate maps that are built in advance to enable them to position themselves very precisely and help them better explain the data. And so this is a map using a robot driving around the second floor of a data center where my lab is. So here's just a picture, a bigger view of it. So this is with stereo camera data. The problem of SLAM is a bit like pulling yourself up by your bootstraps, because to build a map you need to move because your sensors only give partial information. But when you move, you induce uncertainty in your motion. So there's sort of this which came first, the chicken or the egg problem. The motion, estimating your motion, or estimating the structure. And in preparing for this talk, I've been looking at the cryo-EM literature, and I actually believe there's a pretty profound connection to cryo-EM. In the Joachim Frank's Nobel laureate speech, he talked, I wish I memorized the quote, but this sort of the magic, he didn't use the word magic, but that's my word, of concurrently estimating the structure of the molecules and the rotations. And hopefully I'll get to that at the end, the connection. So a lot of my career is built on trying to do SLAM underwater. We test our robots out in the Charles River at the MIT Sailing Pavilion, and over the years we've done various experiments with colleagues around the world, and using sonar, for example, underwater. And back in 2006, 2007, my career took a really interesting turn when I got involved with the DARPA Urban Challenge. So I was a team leader for MIT with some amazing faculty colleagues like John Howe and the late Seth Teller. And we had a big team of postdocs and students. Our robot tried to build maps as it traveled and used a very aggressive motion planning strategy. So here, I don't have the time for the details, but the people in that picture, it's almost like the DARPA challenge pictures, venture capitalists refer to them as like oil paintings. If you're in one of these pictures, you're very well positioned for getting VC money today. And in fact, quite a few of our former students have startups and are being very successful. To make a very long story short, it was $2 million for first place, $1 million for second, $500,000 for third, nothing for fourth. We came in fourth. And I don't really have time to show this, but if we could bring up the volume. Dean Huntenlocker, I think, had to leave, but this is the MIT Cornell Club. Let's see, we're going to go back. Let's try if this is going to play. Now, can you click on the video in the back if you can? Okay, and raise the sound. So this was about 5 hours into the roughly 6-7 hour race, and MIT was, just click the little arrow, please. So I usually have my own laptop, and if it doesn't work, oh gosh, okay, some sort of laptop switching problem. So anyway, it's a long story, but our robot collided with Cornell's robot, and in fact, Dean Huntenlocker was one of the PIs on the Cornell project, and so you can look it up. We actually wrote a 38-page peer review accident report, journal article, about this collision and a few other collisions that happened. It's very funny if you see it online. So my Huntenlocker number is 1, Vladimir. So if you asked me back in 2008, 2007, the DARPA challenge, even though a number of robots finished the race and they let us finish even without this incident, I would have said we were a very long way towards driving, say, in the streets of Boston, fully autonomously. And I still think it's a long way. But Google came along. This is from 2011, the Google founders. And if what Google did is they hired the top people from the DARPA challenge teams from Carnegie Mellon and Stanford and had a secret project where they started driving autonomously with a human driver always at the wheel ready to take over. And over time, the robot learned to drive quite capably. And I got to ride in the Google car back in 2014. This is with one of my PhD students, Ross Finman, who's a whole story. He actually he dropped out of his PhD, sadly, based on the Dean's Sandbox funding. He did a little startup project called Escher Labs that was then bought by Niantic Labs to do virtual reality, do SLAM basically for Pokemon Go. So Ross is the first Sandbox recipient who's now donated money back to MIT. And I said back then that, I felt like I was on the beach at Kitty Hawk, riding in the Google car. And it's really amazing how well it seems to work. And there's a whole industry that's taken flight. And the potential upsides and benefits of self-driving, you could truly disrupt the transportation industry. My big motivation is safety. I'd love to eliminate traffic fatalities, traffic accidents. But you can imagine rethinking the whole way that goods and people move around the world, around cities. So that's why there's so much investment. But there's also a lot of challenges. And so typically when I give a talk, and I couldn't resist today, I talk about some of the challenges, and I hope my videos play. This is a left turn across traffic. This is in Newton, Massachusetts, near where I live. And I'm just trying to make a left turn without a traffic light. And if you look to the right, you can see cars as far as the eye can see. This is at school drop-off when it was a bitter cold day. And if you look to the left, there's an occlusion. There's a mailbox, a tree, a telephone pole. And so to execute this turn, I have to sort of solve a physics problem, the sort of gap estimation, time to collision, but also a social negotiation of waving at another driver to let me in. And sometimes in Boston, the drivers don't let you in. And so John Markoff of the New York Times called this the social ballet of driving. And another example, this is driving through Coolidge Corner in Brookline. This is you can see a police officer is waving me through a red light. And then at the next intersection, another police officer is going to stop me at a green light. So he just sticks out his hand, and I know to stop. And for anyone who's a computer programmer, how do you write the code that says always stop at red lights unless there's a man on the side of the road who's a police officer who's waving you to go through the red light? So this is the same intersection, a different time of the year. I'm sure this is hard to see in the back, but what do you see in this picture? You can see the sun, you can see the traffic lights. It turns out there's a police officer standing right in front of my car. On my screen, you can see the shadow of his legs. And he was directing pedestrians across, even though the light was green. Now, going back to sort of SLAM and why it's sort of important, not for all of these challenges, but the Google car, this is a video from around the time when and by the way, I think Google and their spin-off Waymo are just amazing, absolutely just amazing technology. They're by far out in front of everyone else. But the way that it's been said that any sufficiently advanced technology is indistinguishable from magic. Rodney Brooks always reminds me of that from Arthur C. Clarke. But my sort of addendum to that is that magicians don't always reveal their secrets, but there are secrets to the magic. And having a very accurate map is the secret, one of them, to the self-driving car. And so Google Drive manually around an area very many times, fuse all the data together in a process of SLAM, and then have a very accurate, in this case, intensity map of the reflectance of the road surface that can be used to precisely guide the car, and also to predict where should it see the traffic lights, where are the crosswalks. It still has to handle the unexpected. For example, Google once encountered a woman in an electric wheelchair chasing a duck with a broom, and they handled it. They stopped. But we can't deal with the unexpected unless we have a notion of the expected. And obviously there's difficult weather conditions, so this is driving across Mass Ave a few years ago, walking across Mass Ave on a day. And snow is bad not just because it makes the sensing challenging, the traction, but also it removes the ability to see the road surface, so you lose the map. You lose the sort of precision motion estimation. So for these reasons, I'm kind of a big skeptic or contrarian. I think it's going to take a lot longer due to maintaining maps, interacting with people, adverse weather, and getting really robust computer vision. How do we strive towards very, very, very high detection with very low false alarms? And just briefly, in autonomy, if anyone here has a Tesla, the Tesla autopilot's an example. In Silicon Valley, nearly every hand shoots up. In level 2, you have to be ready to take over at a moment's notice. And humans aren't really good at monitoring autonomy systems. But for level 4, where there's really no human at all, then you really need to strive for near-perfect detection with very few false alarms. And despite the recent advances in machine learning and AI, a lot of researchers call the problem done when they achieve, say, 90% mean average precision. But how do you get to the 99.999% reliability? So that's a little window into things I think about in terms of the questions of how you build maps and navigate, and then some challenges of self-driving. With my remaining few minutes, I wanted to try to speculate on how does this have to do with MIT.nano, all right? And I actually think there's some pretty cool connections. So let me tell you my personal connection, sort of like a 7 degrees of separation. I have this wonderful grad student. His name's David Rosen, who went to Caltech. He's back here now as a postdoc in Lids. And David did some deeply mathematical work with Luca Carlone as a new faculty member now in Lids, and a collaborator from Princeton, Afonso Bandera, who's now faculty at ETH. And it turns out that when you move a camera around the world and you have uncertainty in your rotation and your translation, it turns out that it's a very, very challenging non-convex optimization problem. It's sort of a statistical inference problem in which you can't represent the world as Gaussian, and there's lots of sources of error. And it turns out that folks in the mathematical community, motivated by problems such as cryo-EM, have sort of started attacking this problem because some of the algorithms of interpreting, for example, cryo-EM images, it turns out to estimating the rotations of molecules. And so rotation of the camera, orientation of a car driving on Storo Drive, orientation of a molecule, the math doesn't care that the scale is so small. And so Afonso's a co-author on our paper, which what we can try to do is strive to certify the correctness of an answer. So instead of having a human that's always verifying the answer, could you automatically verify reconstructing complex shapes of molecules? And so our paper with, this is our paper with David, Afonso, Luca, work that I'm really proud of. We're trying to do what they call synchronization. And for a SLAM algorithm, sometimes these are some simulated worlds where there's sort of a sphere. Imagine a robot that lived on a sphere and it was trying to solve for its motion. The challenge in SLAM with this pulling yourself by your bootstraps problem is all the measurements are relative local measurements. So how do you build up a global picture from local measurements? And I think this can apply at the nanoscale. And it turns out that it's very easy as the noise levels increase that instead of getting a nice reconstruction of a sphere or a torus, you get this sort of crazy gobbledygook. And a lot of times as researchers in robotics, when the robot messes up, we just sort of throw the data out. But how could we imagine if we could just in situ observe very large molecules and build up pictures over time? So some other work I was involved with years ago, and this is a whole other story. There's an author here, Tom Whelan. He now works at, this connects back to the augmented reality. Has anyone seen Facebook's live maps? So Facebook Live Maps, they just released a video last week. If you look for Richard Newcomb, he's a student from Imperial College who his startup got acquired by Facebook. It's basically the SLAM, this sort of really amazing 3D SLAM team at Facebook. And one of their guys, Tom Whelan, was a collaborator of mine from Ireland, a student, and he did this work we call Continuous, where using an RGBD camera, a range depth camera, you can, this takes Kinect Fusion, which was developed by Microsoft, and makes it spatially extended with loop closures. And what we can do is we can build really rich 3D dense models. This is hard to see, but it's an apartment in Ireland. This is part of the data center doing loop closing for the very first time with this kind of data. And let's see if this video plays. Oops. See if you can click on that video. If it doesn't. And the goal is that, so what would it take to build just spatially extended, like not go for, instead of just one molecule, try to get entire cells, try to get a picture of everything that's happening at scale. I'm sorry about the movies. I always love to use my own laptop. So So my last 10 seconds, I think there's actually a connection in the math and the way of thinking. Could we apply autonomy and robotics at the micro-nano scale to do this sort of dense, rich reconstruction? I think we can do it if we work together.